Welcome back. As promised in the previous video, I said we're going to talk about math in this video, and the math that we are going to talk about relates to equilibrium constants, and in this case it's going to be equilibrium constants of acids mixing with water. So here is a generic equation of an acid. This is supposed to be an acid, but it's a pretend acid. This A doesn't really mean anything. It basically means just some other elements are part of this formula, and this is the H that's going to get donated as an H plus because that's what acids do. Like I said, this A is just a placeholder for some other stuff. So this is just a pretend acid. We mix it with water. This H plus is going to get donated to the water. Once the H plus gets donated to the water, the only thing that remains from our pretend acid is the A, and it's going to have a negative charge because it donated an H plus, and the water is going to turn into H3O plus, which I said before is called a hydronium ion. And in this case I have a two-way arrow, which is implying that whatever this acid is, this pretend acid, whatever this pretend acid is, it's a weak acid. But let's pretend that we don't necessarily know whether it's a weak or a strong acid. What we could do is we could look at the equilibrium constant for this reaction, and if the equilibrium constant, so if the KEQ is a really big number, that means the right side of the equation is favored, and that would mean that this would be a strong acid. That would be true, let's say, if the equilibrium constant were really big. Then we could also say, well, if the equilibrium constant is small, then that would mean that the left side of the equation is favored, and that would mean that this acid, whatever it is, it's not so strong, maybe it's a weak acid. That seems like a reasonable thing to propose, and we could write the formula for the equilibrium constant for this reaction, and it would be written like this. It's the concentration of the stuff on the right side of the arrow on the top multiplied together, divided by the concentration, the equilibrium concentrations of the stuff on the left side of the arrow on the bottom of the fraction, also multiplied together. And again, you would think that this would be a reasonable way of figuring out whether an acid is strong or weak. In other words, is the top side favored or is the bottom side favored? There is a problem with this though, and it's not something that I would expect you to know. The problem is that once you reach equilibrium, the concentration of water in most solutions that have acid dissolved in them, the concentration of water is enormous. It's a huge number compared to all of the other things that are in this equation. If you look at the molar concentration of water, it's going to be over 50 molar. And the concentration of everything else in this formula is going to be really small compared to that. At the most, it's probably going to be 1 molar, but it could be 1 times 10 to the negative 2 molar. Every other number in this equation except the water number is going to be really tiny. And what that means is this water concentration is going to drown out all of the other numbers. It's just going to dominate. And since it's in the bottom, no matter what you do to measure the KEQ number is always going to be really small, even if you have a strong acid. And so the KEQ equation is not the best way to look at an acid and figure out whether it's strong or weak. And believe it or not, what chemists do to fix this equation is they just throw out the water, and they do a calculation just without including the water as part of the equilibrium constant. But this is not an equilibrium constant anymore if you throw out the water, but it has its own name. It's called Ka, and the A stands for acid. And if you look at this formula, it's the same formula as the equilibrium constant, but just with the water thrown out. So the common abbreviation, or the common way to say this, is we are measuring the Ka for this reaction, the Ka for this acid. Ka has a longer name. It's called the acid dissociation constant. Dissociation just means breaking apart. So this is the preferred way of measuring how much the H and whatever it's attached to like to break apart from each other. That's what dissociation means. And it's just the equilibrium constant with the water thrown out. And there is a general rule of thumb that if you have an acid and the Ka is bigger than 1, then you say that you have a strong acid. If you have an acid and the Ka of your acid is less than 1, then you say you have a weak acid. I'm not sure what you say if the Ka is equal to 1, but that's probably a pretty rare event, so we're not really going to talk about it. You should know what Ka is, how to calculate it, that sort of thing, and how to interpret whether you have a strong or weak acid. You can do the same thing for bases as well. So over here what we have is, this is what I'm going to call a base. Again, this is a pretend reaction. X isn't really a molecule or anything like that, but I'm just saying X is a placeholder for any particular base. We mix it with water. Every once in a while, one of the water molecules is going to donate an H plus to the base. So the H plus is going to go to the base. If it goes to the base, it's going to turn the base into HX plus because it received an H plus. And the water is going to turn into hydroxide, which is over here. And again, there are different kinds of bases. There are bases that are really good at receiving H pluses. Maybe this is really good. Maybe it's not so good. And same kind of thing, you might think that you could measure how good a base is at receiving an H plus by using the equilibrium constant. And the equilibrium constant for this reaction here would be what you would expect. It's concentration of OH minus at equilibrium times the concentration of HX plus at equilibrium divided by the concentrations of the things on the left side of the arrow at equilibrium, all multiplied together on the bottom there. But you know what I'm going to say. The water concentration just drowns out all of the other numbers, and it makes it hard to interpret whether you have a strong or weak base based on just the equilibrium constant. So what do chemists do? They toss out the water concentration from this equation, and they call it something else. They call it Kb. And you probably can guess that the B stands for base. So this equation here is called the base dissociation constant equation. It's just the equilibrium constant with the water thrown out. Same general rules apply. If the Kb for your base is bigger than 1, then you say you have a strong base. If the Kb for your base is less than 1, then you say you have a weak base. And you should know what Kb means. You should know the general formula for Kb, and you should know how to interpret whether you have a strong or weak base using the base dissociation constant. Over here is a sample problem. It says you have 0.1282 moles of uric acid, and here's the formula for uric acid. And this red H is the only H that uric acid is capable of donating. It has some other hydrogens, but those don't get donated. And so you add 0.1282 moles of uric acid to 1 liter of water, and it says assume the final volume is still 1 liter. So we add a little bit of uric acid to a liter of water, does not change the volume. Then it says at equilibrium the concentration of uric acid is 0.1239 molar, so it started at 0.1282, went down a little bit to 1.1239, and it says that the equilibrium concentration of its conjugate base, this is the conjugate base over here because it lost the H plus, is 4.073 times 10 to the negative 3 molar. Then there are two questions. What is the Ka for uric acid? Probably should say under these conditions. So let's pretend that, let's pretend that this reaction takes place at 25 degrees Celsius. So what's the Ka for uric acid at 25 degrees Celsius? And then the second question is uric acid a strong or weak acid under these conditions? So you can pause the video and try to work through that. There's a little bit of trickiness, but maybe not something super crazy. So unpausing the video, it helps to write the equation for the reaction of uric acid. So here's uric acid with water. Uric acid is going to donate this H plus to water, and this is going to be the conjugate base for uric acid right there. And then the water is going to turn into H3O plus. So that's the reaction. I have a question mark over the two-way arrow because we don't necessarily know whether this is a strong or weak acid at the moment. And we need to calculate the Ka for this reaction. So it's going to be the concentration of the conjugate base times the concentration of the H3O plus divided by the equilibrium concentration of uric acid. And remember, we don't count the concentration of water with the Ka. And now it seems relatively straightforward. We need the concentration of uric acid down at the bottom there. Well, we have it. It's going to be 0.1239 molar. We also need the concentration of its conjugate base, which is up in the numerator. Well, we've got that too. 4.073 times 10 to the negative 3 molar times the concentration of H3O plus at equilibrium. Now we don't have this at the moment, at least it's not spelled out, but we can figure it out pretty easily. We can figure it out by looking at this equation up here. And if you look at this equation basically says, look, every time you make one of the conjugate bases, you have to also make an H3O+. What that means is, if the concentration of the conjugate base is 4.073 times 10 to the negative 3 molar, well, the concentration of H0+ has to be the same, because every time we made one of the conjugate bases, we made one of those. So H3O+ concentration also equals 4.073 times 10 to the negative 3 molar. So in place of that, we're just going to write 4.073 times 10 to the negative 3 molar again. And if we multiply through and divide, that will give us our Ka. And assuming that I did the calculation correctly, I get Ka of 1.34 times 10 to the negative 4. So that's the answer to the first question. Second question is uric acid a strong or a weak acid? Well, this is a really tiny number. It's much smaller than 1. So we would say that uric acid is a weak acid under those conditions. So there's a sample problem related to Ka. What you should know how to calculate Ka and Kb, and you should know how to use them to measure the strengths of acids and bases. So that's the end of this video. See you in the next one.
As I was walking down the street last night, a pretty little girl came in the sight. I bowed and smiled and asked her name. She said, "Hold it, bud, I don't play that game." I reached in my pocket, and to her big surprise, that was Lincoln staring her dead in the eye. On a greenback dollar bill, just a little piece of paper coated with chlorophyll.